What I'm going to talk to you about today is a topic very near and dear to my heart, namely tailoring hydrogel surfaces. The people who are actually have done the work in the course of this ERC project have been Rox Simic, Joydeep Mandal, Yvonne Grombert, and Kaiwan Zhang. The group was a mixture of physical chemists, materials scientists, and synthetic polymer chemists. So I'll start off by talking about imitating cartilage, which was the topic of the ERC project. Go on to introduce polymer brushes, brushes on gels, which is the way we imitate cartilage, something on characterizing gels, and this is where AFM comes in, and then talking a bit about the mold effect in hydrogels. We've been dealing with an old dogma on molding hydrogels, and we think we found the answer in the end. So first of all, imitating cartilage. As many of you know, cartilage is an extraordinary material with amazing tribological properties. And the purpose of the project was to try and imitate it using polymer building blocks. And most of the people in the cartilage community are in agreement on, well, a few things. They're in disagreement still on a lot of animated arguments about the structure of cartilage, but most of them are in agreement that on the top of this very complex, amazing material, it actually has no blood vessels in it, so it's quite an unusual biological material. On the top of it is a surface gel layer, very soft, and on top of that is an even softer layer of dangling chain ends, mostly polysaccharides. And this plays a major role in the way in which the cartilage lubricates. And our idea was to try and use polymers to achieve a similar effect, partly to understand more about cartilage and partly to be able to develop new materials based on the principles of cartilage. And we also wanted to use a brush layer, but a polymer brush layer, some kind of gel layer, and maybe using a double network gel to imitate the underlying solid cartilage. Now, polymer brushes are an important part of the whole project and something we've been working on for the last 20 years or so. And just a very quick introduction to polymer brushes. They involve anchoring polymers at one end to a surface and putting them under a good solvent. If they're in a poor solvent or if they're dry, then they crash down onto the surface, and we call this the pancake configuration. If they're hooked onto the surface and they're widely spaced, we call this the mushroom configuration, because they're partly looking like the way they do in solution in the good solvent, but they're restricted in motion because of the anchoring. Just see if I can get my spotlight back. Okay, got it. And then if they're closely grafted, then the interaction with the solvent is more energetically favorable than the interaction between the polymer chains. So they try to keep away from each other and spend more time with the solvent. And this means they have to stretch out against their entropy elasticity, and they form this brush-like configuration. Here are some tribologists imitating polymer brushes. You may recognize at least one of them. So where we started in this game was using this molecule called polyl-lysine grafted polyethylene glycol, or PLL-PEG, and it's a lot less frightening than it may look at first. It's just a whole bunch of amino acids hooked end to end, all the same amino acid. It's lysine here, and lysine has this characteristic of an NH2 group. In water, that will pick up a positive charge, but we can also use it for functionalization. So on some of them, we hook on this long peg chain, some of them we just leave so that they retain their positive charge. And in the end, it looks something like this. We have the backbone, we have the positive charges, and then we have the peg chains. If the positive charges see a negatively charged surface, for example, many oxide surfaces, including silicon oxide, the positive charges will stick down and the chains will dangle out into the solution. So spontaneously, we can form a polymer brush by dipping a silicon wafer, for example, into a solution of the polymer. And this is where we started in polymer brushes. And it's also biocompatible. It's resistant to protein absorption, and so a very useful molecule. This will amuse some of you. This is how we started doing AFM with a colloidal probe. We had no idea about how to make these things. We now make them in all kinds of varieties and materials using springboard tipless cantilevers. But in those days, we bought this cantilever with the colloidal probe mounted next to a sharp tip for some reason. Well, that's how we started. We don't do that anymore. Also, a bit of a historical note, we were making measurements on PLL PEG on the surface with LFM a long time ago. You can see the date of this paper. We have arbitrary units here. Rob Karpik had not yet had his sabbatical in our lab and taught us how to calibrate. So these are in arbitrary units, but I'm just comparing things here. So we see friction against load. So we're looking at the slope as a friction coefficient. And what we can see from this slope here is that we've got some friction in water and also in buffer solution in the case where we have no polymer present. When we have polymer on one side, we lose the adhesion component, but we still have friction. And when we have polymer on both sides, still in HEPIs in this case, we can actually not measure the friction at all. So polymer brushes are extremely effective at lubrication. And in this experiment, we were actually below the level of detection of our AFM instrument. And what's going on here, and this is stuff that came out of Jacob Klein's group a long time ago, is that we have two sets of brushes with some forces acting. We have an osmotic pressure that inhibits the compression of the brushes, and we have entropic forces that inhibit the overlap of these brushes. And we have a fluid film at the interface that isn't obvious here, but modeling and neutron experiments have shown that actually the distribution of monomer going out from the surface to the interface here falls off parabolically. So you have a maximum in the solvent concentration in the middle, and that's where you get the lubricious layer. That is the lubricious layer that gives you the low friction. Now, brushes on gels. This gets us more in the cartilage direction. And first of all, a word on bulk gels, and this is the work of Yvonne Gombert. In the literature, you see a lot of very diagrammatic illustrations of gels looking almost like sodium chloride, or you get depictions of gels that seem to avoid dealing with the surface at all. What we're interested in is the surface of the gel, and we think what's going on there is that on top of the gel, we have dangling chains. No matter how it's made, it's very unlikely that it's going to be significantly, that it's going to be perfectly terminated at the surface without any kind of chains that are not cross-linked. So we believe that all gels to some extent have dangling chains on the surface, and that extent of dangling chains is what leads to the lubricity, the degree of lubricity of the gel. Now, this is quite a busy slide, but let's start from the top left. This is the material that I'm going to be talking about mostly today, polyacrylamide that we make in a very simple way using UV polymerization. So it's a cross-linked system. It's about 95% water. And what Junping Gung in Hokkaido University found about 20 years ago is that depending on how you mold it, depending on this mold surface, you get different behavior on the surface of the gel that was in contact with that mold. And this is some work we did, just extending what she did using a whole bunch of different mold materials. And you can see in all cases, except for glass, with all of these polymers, we got a much softer surface when we indented using AFM. So we use our colloidal probe AFM as an indenter. And I'm going to be talking about many of these kind of experiments. So this is how Junping Gong, and we believe the surface of the hydrogel is when it's been molded against glass. So very little dangling chains, and then against the hydrophobic surfaces we have these dangling chains. And we've looked at this in IR as well. As you push these different terminated surfaces down onto an ATR crystal in IR, you get different behavior, and you start to see these amide signals changing in the case of the dangling chains, but they don't change in intensity in the case of the fully cross-linked gel. So the glass molded one doesn't change when you press it down. So this confirms what Junping Gung has suggested, that against hydrophobic surfaces, we seem to get dangling chains. Now, there's also a time dependence. On the glass surface, obviously, there's not much time dependence because there's not much change. But the change you see in the case of the dangling chains has a time dependence of minutes, time constant of minutes, due to the slow exudation of the fluid from this rather open region where we have the dangling chains. So that's the elastic modulus. It seems empirically to correlate with the mold contact angle, so with the hydrophobicity. Now, the friction we're measuring here on a macroscopic scale, the frictional differences are also great. And we notice something interesting in the case of hydrophobic systems. So POM is somewhere in the middle, but in the case of hydrophobic systems, we don't see any speed dependence of the friction coefficient, whereas in the case of glass, we see a strong speed dependence. And if you look into it, it seems to go as the square root of sliding speed. And there are reasons we can explain for this due to the hydrodynamics of the system. We would expect that for something that has more or less solid surfaces, that this separation would go with speed more or less to the square root. But in the case of the dangling chains, because we're getting no speed dependence, we believe that what's happening as we go faster and faster is that the moving part of the fluid extends further and further down into these dangling chains, and it compensates and gives you a no speed dependence. Now, the question is it really contact angle? And what first alerted us to this is we took glass and we made it hydrophobic. And we took polystyrene and we made it hydrophilic. So the hydrophobic was OTS on glass, so silanes on glass. Hydrophilic, we used plasma. We find that this is exactly the same as the untreated polystyrene. This is exactly the same as the untreated glass, although we've drastically changed the contact angles. So in other words, it's not really contact angle. It's not just hydrophobicity. So we started to look into other possibilities. Could it be thermal conductivity? And the way we looked into this is we did one-sided polymerization against membranes above a water heat sink in order to maintain the temperature at the interface. And we found that irrespective of the thickness of the polystyrene, we saw no difference. This means that even though we were shielding this side more and more from the water, we really saw no difference. So it didn't seem like it was a thermal effect. We thought maybe it's oxygen diffusion from and through the polystyrene sheets. And the way we tested that was doing two-side polymerization with different membranes. And we found that the thicker the polystyrene membrane, the softer the surface. In other words, that was pretty clear evidence that although there was no evidence for thermal effect, the more polystyrene we had there, in other words, the more dissolved oxygen was present and could diffuse out towards to the polymerizing gel, the softer the resulting hydrogel, so the more dangling chains. And the killer argument was really when we used PVDC, probably better known to you as Saran wrap, which is very low oxygen permeability polymer from Dow Chemical. It's hydrophobic like most polymers. However, it behaves just like glass as a molding material. So that really confirmed this idea that it was the oxygen that was causing this mold effect. And if we have polyethylene in there, maybe sitting on a polystyrene surface, which we know is full of oxygen, then polyethylene allows the oxygen to diffuse through. The PVDC does not. And then we also did experiments just to confirm it. We deoxygenated polystyrene and then backflushed with nitrogen. We found that the longer we deoxygenated it, or the more efficiently we deoxygenated it, the more like glass the polystyrene behaves. So it really seems to be the oxygen diffusing out of the polymers that is leading to this effect. And this leads to a way in which you can actually control the friction on the surface of the hydrogel. You can have a gas flow, for example, underneath and change the amount of oxygen in there. And that, depending on how much is in there, that will control the elastic modulus and therefore the lubricity of the surface. And this means that you can also use something like water down here, another kind of fluid, use a bubbler to control the amount of dissolved oxygen. And then with a very thin membrane that allows oxygen to pass through, you can control the degree of dangling chains on the surface of the hydrogel. And therefore, by messing around with the oxygen content of the fluid underneath, you can choose low friction or high friction or anywhere in between. So you have a tunable lubricity. So I'm helping you get back onto schedule, and hopefully there'll be a couple of questions. So I started off telling you about imitating cartilage using hydrogels and dangling chains in order to imitate the behavior of cartilage. And I showed you one way in which we've done this physical way using a mold effect. We've done many other approaches using chemical ways of functionalizing double network gels, and you can find that pretty easily in the literature. I explained what polymer brushes were, how we think of gels, the way the mold can affect the surface modulus of hydrogels and also the friction. An explanation that it's not due to the hydrophobicity of the mold, but due to the amount of oxygen coming out of the mold and to some extent the rate at which it comes out of the mold. And finally, how this can be used in order to tune the lubricity of hydrogels by tuning the amount of cross-linking in the outer surface of the gel during polymerization. And I leave you with a picture, slightly better gender ratio of my group and Lucio Isa's group. This is Lucio Isa. He's my successor at the ETH Zurich, working in a slightly different area, but we're still collaborating. And some of these people are mine, some of them are his. This was in our final group meeting together in Italy just before the world changed. So thank you all very much for your attention, and I hope there are some questions.